basically what happens when AI models first in cancer detection fail not on average, but for particular groups of patients. So in this presentation, I'll be presenting two papers that approach this idea from complementary angles. One of them focused on detecting subgroup miscalibration in deployed models, and another focused on correcting it. So the unifying framework for both papers is post-hoc calibration. Uh, So in this setting, we're assuming that we have an AI model. It's already been trained on our training data. And now we have some like small like audit data set or calibration data set, we call it. Uh, and yeah, the idea is that we want to evaluate it on this calibration data set and measure its performance. So we're not touching the underlying model. We're essentially just looking at its predictions. Any modification that happens will only happen to the predictions, not to the actual model parameters itself. This is, of course, an important setting, the post hoc setting. In practice, we usually don't have time to change systems that have already been deployed. We don't always have time to go back and retrain. So the question becomes, what can you do after the fact? This first paper that I'm going to talk about asks whether we can detect that a problem exists and locate it. And the second one asks whether we can fix it in a way that's principled and interpretable. So I'll spend most of the first half of the presentation on the detection paper, which was published last year in the Melba Journal. Um, so start with a brief motivation. So with melanoma detection AI, we've had some very impressive results in the last few years. The standard metric for evaluating these models is AUROC or AUC, the area under the receiving operating curve. And AUC is a number between 0 and 1, which measures the probability that your model assigns a higher risk score, a higher probability to a patient who has melanoma than to one who doesn't. So if your model has an AUC of 1, that means that your model is perfect at distinguishing high-risk people from low-risk people. Closer to 0.5 to 0 means that your model is worse at this. So AUC is the standard metric. It's a useful summary of ranking ability, but it doesn't tell you much about whether the actual raw probabilities themselves are meaningful. So the models I want to discuss today, they achieved high AUROC scores, usually around like 0.94, 0.95 on large international benchmarks. So by this metric, they're excellent models, right? But like we said, another issue with AUROC is that it's an average. It tells you how well your model ranks patients overall. It also doesn't say anything about whether your performance is consistent across different subgroups within your data set. And in dermatology specifically, we have pretty good reason to think about subgroups. We know that melanoma incidence, presentation, and the quality of training data can all vary meaningfully across different age, gender, and skin tones. So a deeper issue is that even if we stratify AUC by subgroup, we're still measuring something that doesn't fully capture clinical reliability. Um, in my presentation, I'll be using the words AUC and discrimination interchangeably. Uh, so yeah, model discrimination or AUC tells you whether a model can rank patients, high risk above low risk, like we said before. But in clinical practice, decisions aren't always made using just AUC. Sometimes we want to use the absolute predicted probability. So a clinician using a model that predicts 60% risk is going to make different decisions than one using a model that predicts 20% risk. Uh, and if that probability is systematically wrong for a particular patient population, then the model is unreliable for that group in a way that AUROC might not catch. So this is all motivation for why AUROC is good, but maybe we can do something a little bit more. And this is where calibration comes into play. It formalizes this notion of reliability that we're interested in with predictions. What we say is that if we have a model F, we trained it on our training data, and now we're evaluating it on, either our audit data, our test data, whatever it may be. We say that this model F is calibrated if across all the values it can predict, so all the values between 0 and 1, the predicted probability matches the true event rate. So
Hi
if I take
Brandon,
all
sorry
the
to
patients,
sorry to interrupt, but I don't think the slides are changing. I'm at least on my side, we're stuck on slide 2. Um, could you see if you can reshare? Maybe that will fix the problem. Ah, okay. Yes, there we go. I think it's changing now.
there we go.
Thank you.
Okay, nice. Yep, no problems. Right. So definition of calibration. Um, so if I have a model F and I take all the patients that my model assigned a like zero point 0.3 probability of having melanoma, what calibration says is that of this like 30% group, the zero point 0.3 group, 30% of them should actually develop melanoma. If instead 50% do, then the model is systematically underestimating risk for that group. And it makes it hard to trust those numbers as a clinician. So a further extension of calibration is what's called multi-calibration. Um, this is like a stricter notion of calibration that is getting more and more popularity in the literature. So this is the idea that we want calibration not just to hold overall, but within every subgroup in the data. Um, so on the left-hand side, I'm showing two different figures. Let's focus on the top figure first. Uh, so we have the dotted line that's shown in the top figure. This would represent perfect calibration. Here on the x-axis, that's the different probabilities. So we can group patients together by their predicted probability for this model. And the y-axis is the fraction who had melanoma. So again, based on this definition that we just talked about, we want our model to have this to follow the dotted line as closely as possible. Um, So when you look at this, when you look at the line for the entire data set, it seems like the model is somewhat calibrated overall. It does have some miscalibration at the higher probabilities, but maybe that could be fixed. And then when you split this by gender, you see that men and women follow quite different curves. And neither tracks the perfectly calibrated diagonal. They track it even worse than the overall data set does. Um, so this kind of illustrates the idea that a model can look fine in aggregate while failing in specific subgroups. So the four subplots at the bottom in this second figure are making the same point, but a little bit more sharply. So we see that we start with a model that's miscalibrated. We calibrate it using a calibration method called isotonic regression. And it seems to have fixed the problem in panel B. But then when we look at panel C and panel D, we see that different groups in the data set still have different calibration needs. One is being estimated, the probabilities are being underestimated, and their probabilities are being overestimated. So this type of problem that I'm illustrating in these two figures is what multi-calibration is designed to address. Um, so as you can see, we're going to update our formal definition now looking at the right-hand side of the screen. Before we were conditioning this expected value on just the predicted probabilities P. But now we want to extend this conditioning to not only the predicted probabilities P, but for each of the groups that we're interested in our data set. So this is a stricter notion than just regular calibration, what we call multi-calibration. So this idea is going to play a big role in this first method that I'm talking about. We want to study multi-calibration inside of the data sets that we're interested in studying. The second key part of the method that I'm going to introduce is change point detection and CU-sum test. Most of you will be familiar with CU-sum tests from sequential analysis. They're designed to detect structural breaks in a data sequence. So there's different ways of doing a change point test, and they vary by what change your data you want to measure. For example, you can measure changes in the mean of your data and the variance of your data, in the correlation of some parameter in the data you're observing. And the assumption of a change point test or a CU-sum test is that there's usually some type of implicit ordering to the data, such as the like time of observation, right? Like time series data. That is one possible ordering. The overall idea of change point detection is that if you want to study the distribution of your data, of your stochastic process, you'll be able to notice exactly when the distribution of that data changes. So the example I'm showing on the screen is a very simple example of this. We have some time series data of the Nile River. The x-axis is time. The y-axis is the, I think, overall flow of the river. So you can see here in this data, uh, the flow is pretty stable for decades. And then around the beginning of the 1900s, a dam is built. And then you can see a clear shift in the mean that's highlighted by this dotted line. So this is the type of change that a CU-sum test or a change point detection test can measure in practice. Um, helping us to notice the change in the distribution of our data. So now, combining these two ideas together, calibration and change point detection, um, now I can introduce a method that we use to check for calibration in our paper. This method was originally introduced in a paper from AI Stats in 2023, and here's a brief overview of how it works. So just some notation, looking at this first panel right here, the test of strong calibration. Uh, we want p hat to be our model that we trained. So this is the model that we're trying to evaluate post hoc. And then p naught is the true event rate over some data x. And then what we want to do, you can see that the idea of this method is framing miscalibration as a hypothesis test. So we say that our null hypothesis is that the probability, that someone's predicted probability of melanoma is different from the true event rate, is different by no more than some constant delta, is less than epsilon. So in other words, we're saying that our null hypothesis is that our model is calibrated. That's what is being, that's what we're doing in this statistical test. The question is now, how do we actually test this hypothesis efficiently without having to check every single possible subgroup one by one? So what this paper does is essentially following like a three-step method, and I'll walk through each step now. In the first step, we take a portion of our calibration data and we use it to train an ensemble of residual models. And a residual model is a model that tries to predict for each sample how miscalibrated the main model is. The model that, again, we're trying to evaluate in this post-hoc setting. So in other words, these residual models measure how different the model's predicted risk is from the true outcome. Uh, in the second step, we take the remaining audit data, and for each residual model, we order these observations from the largest predicted residual to the smallest. So this intuition here goes back to like the Nile River example that I just showed earlier. If a miscalibrated subgroup exists, the observations in that subgroup should cluster at one end of this ordering, the end with the largest predicted residuals. So in this second step, we're creating a sequence where if miscalibration exists, we expect to see some type of structural break. Then in the third step, we're running a score-based CU sum test along this ordered sequence. So you can see this in the third panel, the figure right here. The y-axis of this panel tries to capture the test statistic that I'm showing at the bottom of the screen, this summation right here over each of the K models that we have. The idea is that if you're able to quantify the difference between the true model and the main model and the true event rate with these residual models, which in this figure are represented by this G hat, then depending on how big the miscalibration you want to capture, which is represented by gamma in here, then you can run this CU sum, score-based CU sum test, and the cumulative score that accumulates through the CU sum test will indicate when there's miscalibration happening through its critical value. So in this figure, the critical value is represented as the red dotted line, and the test statistic is the maximum value attained across all the K models that you ran from all the residual models. So if this test statistic exceeds the critical value, shown here again by the red dashed line and the star, then we reject this initial null hypothesis we started with, and we conclude that miscalibration exists. And finally, as like a side note, this method is usually done in with cross validation. So every observation gets to contribute in some runs of the experiment as training data and in other runs as testing data. So this improves the power of this statistical test while still maintaining like type 1 error control under weak assumptions. So this is an overview of the method that we use to measure miscalibration in the models that we are interested in doing it for. So I'll give more information about the study design that we used for this. The overall goal that we wanted to achieve with this was doing essentially a fairness benchmark. What we noticed in other papers that had done similar types of benchmarking, They had not introduced any type of calibration metric. And as I've talked about in the last couple of slides, we felt that calibration was a very important measure of reliability of the model and understanding how reliable the raw predictions of the model are. So that's why we wanted to do our own benchmark with the models that we had at hand and the data sets that we had at hand. But we wanted to see what role calibration could play in a benchmark geared towards fairness. So what we did in this study is we evaluated three models from the ESIC 2020 melanoma detection challenge, the top three entries, and we included a standard ERM baseline we trained ourselves. So the key design choice was to evaluate on two data sets. We wanted an in-distribution setting and an out-of-distribution setting. ESIC 2020 was the in-distribution setting because this was the data set that these models were developed for, and Prove AI was a prospectively collected data set from MSK that the models had never seen before. Uh, so a drop in performance on this out-of-distribution data on Prove AI isn't unexpected, but we wanted to measure how big that drop in performance was essentially. Um, so Prove AI is the more important test in this paper. One key difference between the Prove AI dataset and the ESIC 2020 dataset is that Prove AI includes a Fitzpatrick skin tone as a variable, which ESIC 2020 does not. And like I said, it represents realistic out-of-distribution deployments on a new patient population. With another note about FST, Fitzpatrick skin tone, is that we focused on Fitzpatrick skin tones 1 through 4 because Prove AI, the FST types 5 and 6 in that data set are nearly absent, which limits what we can say about the darker skin tones in terms of their performance on these three models that we were interested in. Um, so this evaluation had two parallel tracks. For model discrimination, we were focused on using AU-ROC and DeLong's test. DeLong's test is just a non-parametric method for comparing AU-ROC curves that accounts for correlation between them when the same data generates both curves. For calibration, we used the CU sum procedure that I just described. We focused in our calibration results on the number one model, the first place model of the ESIC 2020 challenge, and two individual models that made up the ensemble of the first place model. The first place model is a combination of 90 different models put together. So we selected two of those models of that 90 from the first place model in the ESIC 2020 challenge. One of these models from the ensemble used metadata during its training. The other did not. It only used the raw images itself. Uh, and so the idea behind this was that we want to examine if including demographic metadata during training changes the calibration behavior at all in these models. Um,
Hi, Brandon. Sorry, I think your slides are stuck again. Are we on slide 11?
yep, we're on 11. We're
Oh,
on
okay.
11.
Good. Okay, just checking.
Yep. Uh, right. And then going into results, a few questions worth keeping in mind. Uh, Number one, do the models that perform the best on discrimination also perform the best on calibration? Number two, does calibration degrade on Prove AI in the same way that discrimination does? Number three, does metadata inclusion make a meaningful difference to calibration, not just to AUROC? Okay, so moving into the results, starting with model discrimination results. Like I mentioned before, we used DeLong's test to make these pairwise comparisons that you're seeing in these two tables. The top half of the table compares the three challenge models against each other, and the bottom half compares each of them against the ERM baseline for the ESIC 2020 datasets. Starting with the top half, across every subgroup on ESIC 2020, the differences between ADAE, which is the name for the first place model, second place and third place are small and not statistically significant in any way. Um, these are essentially equivalent models in terms of discrimination on the data that we used for this table, which was the ESIC 2020 test set. The bottom half tells a different story. We see that all three challenge models are significantly better than ERM across every subgroup with very consistent p-values. So again, the takeaway from this slide is that in distribution data, the top models discriminate well and are very close to each other, and they outperform the baseline, which is more or less expected. More interesting results emerge when we look at the same test, but now done on the Prove AI dataset. The top half of the table now shows more meaningful and significant differences between the challenge models themselves, and in particular between ADAE and third place across several FST and age subgroups. ADAE is generally the strongest, but the gap has opened up in a way that didn't exist before on EC 2020 on the last slide. And the bottom half of this table is even more telling. You can see that third place now fails to significantly outperform ERM on any subgroup at all. A model that looked competitive in distribution has essentially collapsed to baseline performance in a simple out of distribution test. ADAE in second place hold up a bit better, but even they have subgroups, particularly FST1 women and FST2 women, where the advantage over ERM disappears. So this is the picture that is painted with these discrimination results. It's already very interesting, but like we said earlier, calibration can give us an even better view of how the model predictions in general add another layer to this story. So again, here's a sample of our results that we got using the CU sum test that I mentioned before. I included the basic steps again in the top right of the slide here. So the CU sum test rejects the null, ended up rejecting the null for all models on both data sets. Every p-value was 0. Um, so on the left-hand side, we're showing a control chart. So this matches figure 3 in the summary figure that I'm showing in the right-hand top right slide. So what we're looking for here is a sharp rise in the cumulative score followed by a plateau or a drop. And that shape kind of tells us that there's a concentrated, poorly calibrated subgroup rather than diffuse miscalibration spread across the whole data set. And that's exactly what we see here. We see that of the K models that we trained here, a lot of them rise steeply in the first 20–40% of the quantile range, and then they kind of level off, which suggests that a specific subgroup is driving the miscalibration rather than the model being uniformly wrong. Looking at the right-hand side of the screen, we have a variable importance plot. Essentially, the way that this was calculated is after we're able to reject the null hypothesis, we permute each feature one at a time and measure how much the test statistic drops. So a large drop means that the feature was important to identifying miscalibration. And as you can see here in the variable importance plot, age dominates by quite a large margin. Gender appears as a secondary signal. Uh, the feature embeddings that are included with this data are scattered throughout the plot, and their intermediate and their presence confirms that the miscalibration is tied to something the model has learned to encode internally and not just surface level demographic metadata. But this pattern that we show overall, which is for the Prove AI dataset, is that age comes first, and then gender second, and Fitzpatrick skin types usually absent, was consistent across all the datasets and all the model variants that we tested. Um, so just to briefly summarize this benchmarking work that we wanted to do, like you mentioned before, prior work had done AUC focused benchmarking, which was a good step in the right direction, but we felt that that was a bit incomplete. We felt that including calibration as a metric in a fairness benchmark could capture a distinct and clinically important dimension of model reliability or model fairness. The second takeaway is that age is a consistent and actionable finding. It drives miscalibration across models and data sets, and metadata inclusion can partially mitigate it. Third, and I think most importantly for this audience, is that data gaps across subgroups are a fundamental barrier. The FST non-finding with the calibration results is not necessarily reassuring. It somewhat reflects the limited representation of FST types 5 and 6 in dermatology data, rather than like genuine absence of miscalibration. Yeah, in summary, we wanted to include calibration as a metric in fairness benchmarking and see how a state-of-the-art melanoma detection model performs when evaluating its calibration at the same time as evaluating its AUROC. So this kind of leads into the second part of this presentation where uh, we still speaking about post hoc calibration. Before we were in this paper, we were just concerned with detection. So we were asking, is this model miscalibrated for some subgroup? Now we want to focus more on the idea of correcting this miscalibration. So uh, now that we know that a model is miscalibrated, how do we fix it in a principled, interpretable way? So that's what the second half of this talk addresses, and the second paper of this talk will address. So this second paper is ongoing work that we call learning semantically coherent calibration groups. So this is a post hoc method for correcting subgroup miscalibration without requiring those subgroups to be predefined. So let's quickly go back to the multi-calibration reframing. Um, so as we said before, the definition of multi-calibration, it's the idea that we want calibration not just to hold when we evaluate it over the whole data set, but we want it to hold within every subgroup. And here we're denoting subgroups as GK. So the problem, as I mentioned before, is that standard post hoc methods can calibrate a method, tend to calibrate a method globally. So this seems to work as we're seeing in panel B in the bottom figure. But again, when we look at this miscalibration, when we separate the calibration across different groups, we see that the model is still miscalibrated in different ways for different groups. Um, these types of failures are exactly what we tried to address in this second paper. Now that we know when we've studied that different groups in the data have different calibration patterns that need attention, and how can we locate these groups and fix the miscalibration we're seeing? Um, Another challenge that we wanted to overcome with this next project that we work on is that in real world settings, we often don't know in advance which groups we need to correct. Um, Sometimes the groups can be clearly defined, like, for example, we know that we just want to focus on maybe men and women, but other times the groups might be combinations of different groups. So, for example, men over the age of 50 and women over the age of 50. Um, Another setting that can be explored too is that sometimes groups can be defined by their image quality as well as their metadata features. So this could be, for example, men over the age of 50 who have very large lesions in the images that were provided. So this is the motivation that we followed for the second project. What if we want to fix calibration and not just detect it? And what if the groups we need to fix aren't predefined? So focusing on this first question, uh, before describing the exact approach that we followed, uh, I wanted to show what a calibration method looks like. This is one that we used in our paper. Um, so when a neural network makes a prediction, it doesn't directly output a probability. Instead, it outputs raw scores called logits, one for each class. So in this binary case, we have O0 and O1, and these are the scores for the benign and the malignant class, respectively. So to turn these into a probability, we apply the softmax function, which exponentiates each score and normalizes the sum. Um, so the predicted probability for malignancy is what you're seeing as f of x on the bottom right-hand side of the screen. You take the logit for class one, uh, you exponentiate it, then divided by the exponentiated sum of all logits. This f of x is the probability of class one. Um, so one popular recalibration method is what's known as Platt scaling. So Platt scaling recalibrates by introducing two learnable parameters, alpha and beta, that adjust the malignant logit before applying the softmax. So alpha shifts the logit up or down, and B scales the logit. And you can see this formula again in the bottom right-hand side of the screen. It This focuses on the logit of class one only, so no changes are made to the logit for class zero. And just to illustrate the effects of having different varying alphas and betas, I have this table right here, which shows that in a normal setting, if you start with alpha equal to 0 and beta equal to 1, and these are your original logits, these are the probabilities you get. You can see that by varying alpha and beta to different degrees, this changes the final probability that we get for each class. Most importantly, I'll point to the last row of the table here, where alpha is equal to -2 and beta is equal to 0.25. You can see that this has completely flipped our prediction compared to what we originally started with the logits. So now we're predicting that benign is actually the true class for the sample. So this is a very powerful idea. This is a very powerful method in general, not just for fixing this calibration, but for correcting accuracy more broadly. So like I mentioned before, in a standard setting, you would apply something like Platt scaling to the entire data set at one time and learn a single alpha and beta globally. But as we've already talked about with multi-calibration, different groups in the data have different calibration needs. So some are being overestimated, some are being underestimated. So what we really want is a separate alpha and beta for each subgroup. And that brings us to our uh, central challenge. We don't know what these subgroups are. So now let's focus on answering this second question. What if the groups we need to fix aren't predefined? So prior work on this type of group discovery, uh, specifically from a group Yang et al., they approached this by learning group assignments jointly with the calibration. Uh, so we've used this method, but in practice, we've observed that this method suffers from group collapse quite often. So this algorithm finds it easier to assign most samples to a single large default group and then apply like essentially a global correction. Um, and essentially this makes meaningful subgroups effectively disappear. In some examples we'll show later, in some comparisons that we've done, this method puts over like 85 or 90% of the samples into one group. Uh, so we liked this method, but we wanted to find a way to build on top of it. And what we did, the key insight that we used to define our new method is that we wanted our calibration groups to satisfy two constraints simultaneously. We wanted samples in the same group to have similar calibration needs, and we also wanted them to be semantically similar in the model's embedding space. So enforcing both of these constraints together, this was our way of trying to prevent group collapse and producing groups that were more stable as well as more interpretable. So we called our method semantically coherent calibration, and here's an illustration of how it works on this slide. Um, the idea is that as input, we begin with dermoscopic images, and optionally, depending on the type of model you use, text prompts that can describe the clinical context of each image. So you can imagine for each of these four images that we have here, if we had the metadata for these images, we could replace these bracketed pieces of text with the information that's correct for each specific sample, each specific image. Um, the model that we used specifically for this was a vision language model. If any of you are familiar with, for example, like Quen or Lavo, those family of models that can take both image and text as an inputs. So what happens is this VLM, the vision language model, it encodes each sample into an embedding Z of X. Um, then what we do from there is we take a lightweight linear layer. So this is just essentially one layer of a neural network, a linear layer G of X, and we map that embedding to a assignment over K groups. So the idea here is that we're trying to learn these different groups that I'm showing on the screen, the G1, the G2, and the G3. We want to train G of X to be able to give us, if we ask it to give us five groups, then we hope that it's able to produce five groups, five distinct Gs with our method. Um, and crucially, like I've said before, we don't know which sample is going to belong to which group. The groups can be defined by their image characteristics, and they can be defined by some combination of their like metadata characteristics as well. So essentially what our method does in this embedding space is three things. Um, you can see the full loss function is being shown on the screen here. It's called LSCC. It includes a term that's related to a loss term that's related to calibration, a loss term that's related to semantic similarity, and then just a regularization term. Um, so starting with the calibration loss encourages each group's Platt scale predictions to match the observed outcomes. Um, so again, this is again the term that drives the groupings to be more to be defined by the calibration. The semantic loss LSEM penalizes assignments where a sample is placed too far from the group. It's centered in the embedding space. So this LSEM term controls the semantic similarity, the semantic coherence between groups, and tries to prevent random assignments. And then the regularization term just prevents the weights, the W's in our G of X, from growing too large. So together, using these three terms inside of a loss function help to push our method towards groups that are simultaneously calibration coherent and semantically coherent too. And I summarize the steps in the text on the screen. So what we do is for each sample, we find the probability of the sample belonging to each group GX of K. So that's shown in the red. Then we compute its malignant class probability under each group's calibration parameters. This is the alcal term, shown in blue. And then finally, we compute its distance to each group center. And this is the pink term, purple term, LSM. So focusing more on the results of our method now. This slide shows what the learned groups actually look like on ESEC 2020. The tables on the left show the quantitative story, and the images on the right tell the visual one. So starting with our method, we learn all four. So what we did to generate these tables is we took the best seed, the best run of our method, and we compared it to the best seed or the best run of our competitor's method. Our competitor's GC plus TS. So in the and here we define best as the lowest calibration error. So starting with our method was able to learn all four requested groups in the best, absolute best run. And the group sizes are reasonably balanced from about 1,000 to 3,800. We also measured the relative risk of each group. You have each group that we created. We see that for G1, we have a relative risk of 5.79, meaning that our method is learning to genuinely put together the high risk cases into one group. We see that G0 has a very low risk, 0.05. So this is more of like a regular benign group. The alpha parameters of each group kind of reflect the type of calibration correction that each group needs to. G1 and G3 have negative alphas, indicating that the model was overestimating risk for those groups, and the calibration correction tries to shift the predictions downward. And looking at these images on the right-hand side, this lines up visually. We see that G0 is like a small, tight, regular lesions, and G1 is more like large, dark, irregular presentations with artifacts in them. G2 is more dark images, but benign, and G3 contains more complex or atypical cases. And then comparing this to our competitor's method, GC plus TS, in the absolute best run of this method, it was asked to create four groups, but it was only able to create three. And one of the groups, G0, contains nearly 85% of the data set over 8,000 samples. The relative risk of this group is also quite low. So this is essentially what group collapse looks like in practice, where our method was able to learn more balanced groupings that give more interpretability and more meaning to each group. The GC plus TS method collapsed to putting a lot of samples into the same group. The two remaining groups are real but tiny, and the method has effectively given up on finding meaningful structure in most of the data. So the representative images on the right that you see reflect this. The GC plus TS groups have much less visual coherence than ours do. Now, flipping to the calibration results for this method that we ran. So we made three variants of our method. Each of these just use like a slightly different calibration focused loss function. So these are the three rightmost columns that you're seeing. And then the three leftmost columns that you're seeing are the calibration results on our competitor's method, as well as an uncalibrated baseline. So yeah, with calibration error, lower is better. And in this table, bold entries are ones that are not significantly different from the best method. So looking across the rows, our method SCC CE, and CE here stands for just cross entropy calibration loss, was competitive with or better than all baselines on a majority of settings. Um, the most important comparison here is again against GC plus TS. This is our closest related work, closest prior work, and our method consistently outperforms it, um, particularly in the pre-trained settings marked PT, which is like a deployment scenario in which you don't do any fine tuning on the vision language models that we use for this experiment. You simply just take the base model from Hugging Face and evaluate it. Um, so this uncalibrated baseline performs surprisingly well in some fine-tuned settings. Um, this is consistent with what prior literature says that fine-tuned VLMs can be reasonably calibrated out of the box. Um, yeah, the bigger gains for our method come in the pre-training regime, where the model's predictions are less reliable and subgroup-specific correction matters the most. Right. So to wrap up this second half and the core tenet of this overall work, the main takeaway is that jointly optimizing for calibration need and semantic similarity in the embedding space can help to produce stable, interpretable, and better calibrated groups. There's better groups than methods that optimize for calibration alone. So the semantic constraint that we concluded in our method is what helps to prevent group collapse and keeps the learned groups meaningful and interpretable. Um, so looking ahead on future directions for this post-hoc calibration work, uh, so in this, we spoke about two different methods, one that's able to detect miscalibration in a post hoc setting, and another that's able to fix calibration in a post miscalibration in a post hoc setting. Uh, our lab is thinking about two paths forward from these two works. One is to move calibration into the training setting rather than the post hoc setting. So the idea is that if we're able to stop miscalibration during training, then we might not even need to do a post hoc training step. So the question here is how, if we wanted to do again the same type of like a group discovery, for example, during training, how would we be able to incorporate that into a training objective? Um, the other direction is to stay in the post hoc setting, but maybe shift the calibration framework into a different measure of uncertainty. One measure of uncertainty that you all may be familiar with, you may have heard of, is what's called conformal prediction, which is something that our lab is very interested in. Uh, this conformal prediction trades point probability estimates for more coverage guarantees, and it might be a more natural choice in clinical decision-making context where you need like this type of reliable prediction set. But yeah, whichever direction we decide to go in, we note that both directions connect back to the broader goal of the talk, which is building medical AI systems that are not just accurate on average, but reliably calibrated for each patient. So that's everything that I wanted to present. So I'd like to thank you guys again for having me as a guest.
Thank you very much for joining, Brandon. That was a really, really interesting talk. For people watching, you are free to raise your hand and turn on your mic and ask a question, or simply type in the chat. Um, I'll give you guys a bit of time to think, but I have a question for you myself, Brandon. So. I really like how your method is able to learn these groups sort of data adaptively rather than, I think a lot of the time when we think about fairness, all these sort of, what do they call them? Sensitive groups are sort of given to us in the data, but they're usually like a social construct rather than something that's actually given to us, like maybe that's more clinically meaningful. Um, and I was just wondering, how do you choose the groups? Like, how do you decide, it seems like there are four groups in this data set, or is this something that is like a hyperparameter you can tune, or how do you decide on that?
Yep. Yeah. So flipping back to uh, the slide. So the G's are the number of groups that we look to learn is a hyperparameter that we do a grid search over in our method. So we start with two, and then I think we go up to about like five or six.
And then for your in your case, four was the optimal number of groups, I guess.
Yeah, four was the optimal. So in this, in the results that we're showing on the screen, uh, using four groups produced the lowest calibration error, which is why we selected it here.
Cool, thank you. So Joshua asks, it seems there are many hypothesis tests being done implicitly as part of this method. What steps were taken to address multiple testing?
In the sense of multiple testing, if I'm understanding correctly, I can flip back to this slide here. So this would be more focused on like the CU sum test. If I'm understanding your question about multiple testing, what we did is we did a lot of like Monte Carlo testing with this method to basically calculate the p-values through that process. So we simulated the distribution of the test statistic under the null by resampling different outcomes with the model's predicted probabilities. Um, and the p-value is the proportion of simulated statistics that exceed the observed one. So in this CU sum test that I'm showing on the screen here, all the tests that we did across every model and data set produced p-values of zero, meaning that in none of our simulations did the null statistic ever come close to what we observed, which was like strong evidence against the null.
Margaret asks, please could you provide some concrete examples of semantic similarity in a clinical context? Also, could you provide some comments on how your approach for identifying groups compares with cluster analysis? So, two questions in one for you.
Semantic similarity in medical context. So I'll go back to our results actually. So we we look at semantic similarity in terms of any visual coherence in the data. So again, looking at these different images that we have, do they share the same visual features, such as like the same background or the same like lesion size or the same lesion color? So in terms of visual similarity, we also look at metadata similarity. So in this figure, we'd be looking at the left-hand side and looking at the bottommost columns of each table. So this is the type of metadata that we included in the models that we were using to create these groups, create the embeddings, I should say. So the groups would be defined by things such as like their average age, the average, the percentage of men in each group, and then looking at what percentage of samples belong to which location of the body. So that's essentially how we define similarity. Similarity in terms of metadata characteristics and similarity in terms of visual characteristics as well.
And
I'm sorry,
then
what was
the
the
second half
second
of the
question?
question was, can you provide some comments on how your approach for identifying groups compares with cluster analysis?
Um, So our method is essentially a clustering method. That's how we thought of it when we were formulating it. We were very inspired by a lot of ideas from like the clustering realm. Specifically, this looking at the pink term we have here, this loss term. That's a term that comes from like usually classical like k-means clustering. Um, so yeah, in terms of comparison, I would say our method is very comparable to a clustering method. I would say that the main difference between our method and what's done in like classical clustering literature is that the group assignments and learning the groups is done through this function g of x, which is not something that you would typically see inside of a clustering algorithm. Using this allows us to use a fully differentiable loss function, which makes learning the groups like a little bit faster, a little bit easier. If we didn't have this g of x, then we would have to do something like more of like a standard like k-means or like a clustering approach.
And then one question from me again. You mentioned conformal prediction in your final slide. I was wondering what your thoughts on this are, given that conformal prediction doesn't seem to have guarantees, like conditional coverage guarantees. And that's one of I've looked into using some of these conformal methods before, and that's the hurdle I came across. So I wonder if you've thought about that.
Yeah, yeah. We if we do move in the conformal prediction direction, that is something that we want to look into as well. We there's been a few works that we've been able to find that have done a similar idea as what I'm showing on the screen actually, but have applied it in a conformal prediction setting. So you want to achieve conformal prediction for the different groups in your data set, but you don't know how many groups there are. So can we learn the groups while also finding like the right parameters to ensure that each group is as calibrated in a conformal prediction sense as possible? So yeah, that'd be kind of like the natural extension of this work, doing the same type of group discovery, but groups that focus on conformal prediction.
Great, thank you. I don't know, I don't see any more questions, so I think we'll leave it here. But thank you very much, Brandon. Thanks for joining. And yeah, thank you everyone for tuning in today. So we hope to see you next time at the end of the month. We'll have another talk by Amanda Costin. So we hope to see you there. Thank you, everybody.